Good morning, everyone. Myself, Deepantu Chaudhary, Department of Electrical and Commerce Engineering, Hotel Institute of Technology. Today, I discuss about the overview of an optical lithography. Optical lithography is a very important process in fabrication, device fabrication, or MEMS fabrication. Lithography means stone and graphics. Litho means stones and graphics means write a pattern the stone. Optical lithography refers to a lithographic process that uses visible or ultraviolet light to form patterns on the photoresist through printing. Printing is the process of projecting the image of the patterns onto the wafer surface using a light source and a photo mask. So, for lithography has several steps. Number one, coating with photoresist, soft bake, align marks, expose, develop, hard bake each window in film, remove photoresist. So, before we go into the photolithography process, we see that initially we need to design the layout of the pattern, which one we want to print on the wafer surface. So for that we need to PC system where we use the CAD tools. For example, LAS is the software tools for the designing layout of the device fabrication or MEMS fabrications. So when we design the layout, after that we transfer this layout to a photo mask, that is this one. This one is the photo mask where the substrate is the glass and the pattern is making here by the metal. So this marks is called the photo marks, where this patterns or this marks is transferred to the wafer using the exposure method or lithography method. So here we need to make the pattern in the top of the wafer, silicon wafer. We need a silicon dioxide layer. So for that we need to go through the process, that is oxidation. So first we go through this process, that is oxidation, where oxidation two types. One is dioxidation, another one is wet oxidation. In oxidations, the silicon wafer are heated by 900 degree to 1200 degree centigrade through the oxygen and H2O diffuses to the silicon surface. So during the oxidation, we see that the wafer color is changes. Wafer color is changes during the oxidation. So after the oxidation, we apply the lithography process to transfer the pattern to the silicon wafer. So for that, we go through again these steps, that is coating with photoresist, then soft bake, then align marks, then expose, then develop, then hard bake, then each window in film, then remove photoresist. So first we go for the coating with photoresist. So coating with photoresist, where we use a vacuum chuck where the wafer is placed, and after that we disperse the resist on the wafer, resist dispenser wafer, and accelerate the wafer fast, spin at constant speed to get uniform thickness. So typically the speed of the vacuum chuck is 4000 rpm. If we rotate it for the 20 seconds, we get near equal to 1 micron thickness. where excess resist flies off during the rotation. This is the coating with photoresist tapes. In these tapes, we get a layer on the top of the wafer which is for the photoresist. So then we go for the soft baked. So after that we place the wafer in a oven for a 30 minutes in temperature 90 to 100 degrees centigrade. For due to the soft baked improve photoresist to wafer adhesion, promotes resist uniformity on wafer, improves line with control during each, and drives off most of solvent in photoresist. Then we go for the align or expose. So to get the pattern on the wafer, so we use the photo marks and we apply the UV light. So that is for the exposure. This light is passed through the transparent area of the marks and it's fall in the photoresist. Where alignment is required if we need more than one marks to transfer the pattern on the photoresist, then we need to align the marks with the UV light and the wafer. Then development. What is develop? Soluble areas of photoresist are dissolved by the developer chemical. Visible patterns appear on the wafer, that is windows as a windows and as a islands. We go for example, then we show you which type of windows and island. Then we go for hard bake. In this case again we place the wafer in the oven for a temperature that is 120 to 140 degree centigrade. Due to this hard bake, a post-development thermal bake is required. Evaporate remaining solvent due to the hard bake and improve resist to wafer adhesion also. Next step, that is etching. So after that we need to remove the SiO2 layer, that is marks film layer. So each in order to remove the metal that are not covered by the photoresist. Formation of windows in the marks film. Wet etching is remove the material. RIE or ion milling is used to remove this unwanted material. Last is the stripping. The final steps consist of removal of the exposed photoresist. Positive photoresist are usually removed by means of a chemical solvent such as acetone or ethyl ketone. And negative resist are considerable harder to remove. Here, one approach is to immerse the silence in a 1:1 mixture of concentrated H2SO4 and H2O2. So, what is positive photoresist and negative photoresist? We see next slide. In negative photoresist, the wafer image is opposite of the marks image, and whereas positive resist marks image is same as wafer image. In case of negative resist, exposed resist hardened and is insoluble, while in positive resist, exposed resist softened and is soluble. And in case of negative resist, developer removes unexposed resist, where positive resist developer removes exposed resist. So we better understand with this pictorial example, where you see this is your wafer, substrate, silicon substrate, oxide, and top of the oxide, that is photoresist, and this is the marks and UV light source. So this black portion iceland on glass marks. This black is the pattern on the photo marks. This pattern is transferred to the wafer. So if we use the negative resist, the light is passed through this area, transparent area, that is this portion, due to this negative photoresist, this is the hardened, and where the light is not reached, that is your soluble. Okay, so this is your island and this is called window. So area exposed to light becomes cross-linked and resist the developer in chemical. So we get this pattern. This is window, this is island due to the negative resist. Similarly, in positive resist, where the marks is different, where the middle portion is transparent and other portion is opaque, so light is passed through this transparent area. So light reach to the photoresist in this area. So due to that, this is soluble. Where the light is applied, that is soluble, that is your window, and where the light is not reached, that is your island. So in develop when the wafer is developed with the chemical, particular chemical, then we see that this portion photoresist is soluble and this hardened. So next we see that the pattern is exposed to the wafer by different exposure method, that is contact printing, where these marks and wafer or photoresist is in contact, where proximity printing, the marks and photoresist, in between that there is a gap, and in projection printing it's print by the XY coordinate scanning. So we see at a glance that in contact printing, marks and photoresist coated wafer is in contact, and where proximity printing, small gap between marks and photoresist coated wafer is 2.5 to 25 micron. Whereas projection printing, an image of the patterns on the marks is projected onto the photoresist coated wafer, where whole surface is exposed by XY scanning. So in contact printing, edges are very sharp, whereas in proximity printing, edges are not sharp. In case of projection printing, that is see the okay. So here you see the resolution in the contact printing. Resolution is very high, whereas in proximity printing resolution is affected, and in projection printing minimum marks damage or resolution capability is very high, and projection printing the minimum max damage, longer process time in case of projection printing, whereas proximity printing marks life is enhanced, and in case of contact printing marks life is very short. So at a glance we see that the projection printing is take a time more, longer time more, and where the resolution is very high in case of projection printing, and also the marks life is enhanced in case of proximity printing. So next we see that weight etching. Weight etching is a blanket name that covers the removal of material by immersing the wafer in a liquid bath of the chemical etchant. So weight etching two types. One is called isotopic etching, another is anisotropic etching. In case of isotopic etching, we see that the etchant are etched under the SiO2 marks. So for the isotopic etching we use mixture of HNO3 and HFE in H2O. Whereas anisotropic etchant attack the material at different rates in different direction. There is more control of the shapes produced. Each rate depends upon orientation to crystalline planes. Crystal planes of a semiconductor etches faster than other planes. So here you see one plane. Due to that, the each end is each according to this plane. So similarly, here also one plane. Okay, so for that we use anisotropic etching for the silicon is KOH. So this is for the etching. Next, we try to understand whole things, the lithography process with this other process, that is oxidation and etching by this example, where we consider a tunneling accelerometer. This is the tunneling accelerometer top view. To make these MEMS systems or fabricate these MEMS systems, we need different types of photomarks, that is 5 photomarks, that is top marks, tip marks, back marks, metal marks and isolation marks. So here we require more than one photomarks, and these photomarks in software or in PC we make by the CAD tools, that is lashing. Okay, so we see the how to fabricate these MEMS systems or MEMS accelerometer, that is tunneling accelerometer, step by step to understand the photolithography. So where you see, this is the top view, this is the pad, this is called cantilever, this is the base which where the cantilever is attached. So if we see in cross sectional view, where we see this is the cantilever and this yellow color is the pad. Pad means the conductor. So here use number 1 wafer, here number 2 wafer. 2 wafer you use, and after that it is bond. So initially we see for the bottom layer, that is this is the silicon wafer, where we use this pattern. This is the pad or conductor pattern, where this is the layout. This layout is transferred to this silicon wafer by the lithography process step by step. That is first photoresist coating, then soft bake, then expose the light, then go for the hard bake, then go for the develop, then go for the etching, then go for the stripping. Then we get this type of pattern on the top of the surface of the wafer. So this is the wafer number 1. So for the wafer number 2, that is your how to fabricate the cantilever with tip. So first we consider a silicon wafer, that is here for example 100. This length of this is 280 micron. So after that we need to make or from the oxide layer on the top and bottom of the silicon wafer. For that we apply the oxidation process. After that we apply photolithography process, where we use top marks and back marks, means we need 2 marks. So for that we need to alignment and go through the all the steps of the photolithography one by one. So after that we get this window, both side, bottom side and top side, get this window. After that we apply some metal as chromium and Au or gold, and in the top. So after that we apply again these marks, which is called the tip marks, and we go through this process by the photolithography to get this tip. Get this tip. Again we go through all the steps, get these tips, and after that we apply the KOH to each this portion to make a cantilever. To make a cantilever, so here we use white KOH because the KOH for the silicon is by the plane, according to the plane. Similarly, in next we again apply the KOH for more etching to get particular shape of the cantilever. So here we get this one. After that we need to remove the oxide layer in this portion. So that's why we apply the etching process. Here we apply BHF, and next step again we apply the KOH because we need to get the perfect cantilever for the particular tunneling accelerometer and get this tip. Okay, so next we remove the metal from the top layer, and then we remove the oxide layer. Then we get this pattern where we see there is a tip and this is the cantilever. After that we apply the chromium, that is brown color, and then we apply the Au, that is your yellow color. So then it is become a perfectly shape for the wafer 2 for the cantilever. So previously we get the bottom wafer, that is base, and this is the top wafer, that is wafer number 2. When we bond both together, then we get this MEMS structure or tunneling accelerometer, where this cantilever vibration is indicate that this tip electrode and this electrode distance is changes due to the vibration of this cantilever. So when the change of this distance, during this change the tunneling current also change. So depending on the tunneling current we can calculate the acceleration. So this way we fabricate this type of device. Here for example it is your tunneling accelerometer. So here some equipments are shown. So where this is the photoresist spin station, this is the oxidation furnace, whereas here probe station, optical microscope, these are the equipment for the fabrication of any type of device or MEMS. Thank you for your attention.